So in the last part, we actually try to discharge the sequence formulating the deadlock freedom proof obligation. Let's recall very quickly about what we concluded, and then we can connect to this particular part with the more valuable feedback. So this is what we tried to do in the last part of the lecture. So we started with this particular sequence formulating the deadlock freedom proof obligation. And remember, this is something we did using the OR left rule, which is over here that we newly introduced in this week's lecture. And we try to branch out into two independent sequences to be discharged. We were able to discharge the first case with a particular hypothesis. But for the second hypothesis over here, we kind of failed to actually discharge the sequence. We tried either one route or we tried the other route. And also I spoke about intuitively, like which route should be more worth our attempt, right? That's something we talk about this one here. Should be a more reasonable fix than this one over here. You can definitely review the last part of the previous video just to make sure you understood. Right, so let's now continue with our discussion, which will be how can we interpret this particular failure in the proof. So whenever you actually try to do things formally, and if you somehow get stuck or you simply just cannot really prove something, that should really give you some very valuable feedback about how you can go back to your original specification and see what you can do with it. That's exactly the reflection process that I would like to discuss right now, which is equally important to the proof themselves. So don't lose the big picture. The reason that we are trying to do proof is to really argue that our model M0 is actually provably correct with respect to deadlock freedom. If somehow the proof obligation cannot really be discharged, that means our original model may have some flaw. In that case, we definitely have to fix it, right? Proof is just a communication tool to really help us getting some useful feedback, but it's not the end, right? Right, so why do we really fail to discharge the proof obligation for deadlock freedom? Let's now discuss it. Right, so in our first attempt, which I just showed to you, the proof of the second case actually failed, which is this particular sequence. Again, once more, this is the sequence, this is the part I'm talking about for the constant d larger than 0, right? That's the one that we actually failed to prove. Okay, wrong way. And what we want to do now is to really see what kind of a feedback or hints this fail sequence actually will give to us in order to fix our model. Let me talk about it. And I'm going to talk about the different points, which I will definitely mention in the writing, the bullet points in the slides. But I'll let go over them with you quickly over here on the page. Right? Let's write some notes together. Okay. This is our model M0 as is, and this is our abstraction for the initial model. Right? Just make sure you understand the context. And this is something that we failed to prove, which is about the constant. Well, if you look at the sequence over here, d larger than 0, and the d is definitely declared as a constant over here, and the only constraint that we know about for d is its typing constraint, which is d is actually a natural number. Okay? And you should really know implicitly when we say d is a natural number, that means d would be larger than or equal to 0. Right? That's what we know. Meaning that there is a possibility that d might be just equal to 0. That could be what the issue is, but that's something we're going to see. Okay, so let's now go over some, just try to interpret this particular feedback. We know that this one cannot be proved. So what does that mean? So we know that basically we cannot really prove that our model is deadlock free because this particular sequence failed. So that means it is not the case that d is larger than 0. Is actually possible for our model. It's possible for our model M0, right? We try to prove this, but somehow it cannot be proved. We try to prove d larger than 0 as a goal, but somehow it cannot be proved. So that means its negation is actually allowed by the current model, right? Meaning that it's not the case d is larger than 0, right? Just make sure I understand why I'm writing this negation over here. And we know that this part over here is equivalent to d less than or equal to 0. So according to the proof process, we learned that our model currently is not deadlock free because it is possible that d is less than or equal to 0. To be more precise, we know about there is one single constraint for our constant. That's in the axiom over here, right? So let's combine this. So this will be number 1, and for number 2, we know about the axiom. So the axiom for model 0, number 1, is d is actually a natural number, right? Meaning that d is actually larger than or equal to 0. If you try to combine these two together, right? This is what we know from the existing declaration, the existing specification of our model M0. And this is what we know will be allowed by the fail proof, right? So understand the rows for 1 and 2. And what can we conclude from 1 and 2? We can actually conclude from 1 and 2 over here, less than or equal to 0, and also larger than or equal to 0. What does that mean? That means it is allowed that d is equal to 0. That's really the boundary case that we may want to watch out for, right? So that means d is equal to 0 is really the cause for some deadlock or some blocking, right? So this is something we can conclude as the reason, the scenario, like a counter scenario for deadlock freedom. Our system would not really exhibit deadlock freedom because of this particular counter scenario, right? It's really important to see how I draw this conclusion for deadlock freedom. All right, hopefully so far so good, right? It's really important for you to understand how to really interpret any failed sequence later and try to do some analysis accordingly, right? Deadlock freedom, all right? And what can we go from here? And I would like to show to you why this should be considered as a counter scenario, right? That's something I would like to show to you. Okay, let me use maybe purple over here. Let's see exactly what happens if d is equal to 0. When d is equal to 0 over here, that's where the deadlock is going to happen. Deadlock happens. What is that? So what's our definition for deadlock? Deadlock simply means all the events are disabled, meaning that their guards simply evaluate to false, right? Let's now highlight them over here. This is the guard for ML out. This is the guard for ML in. So why would both of them actually evaluate to false, meaning that both events will be disabled? Let's see exactly why. Okay, so I'm gonna just copy this expression over here and also this expression over here. So n less than d or n larger than 0. Remember, according to our proof obligation rule, we're going to disjoint all the guards for all the events together, right? And we are talking about a particular scenario where d is simply just equal to 0, right? So d will just be replaced by 0. And there's only one occurrence. What about n? So n over here, so we are talking about n less than 0 or n larger than 0. So these two propositions may not necessarily evaluate to false always, but there will be some particular scenario. There exists one value for n such that both propositions will just be evaluated false. What would that be? Well, for example, when n is equal to 0, and when is n is equal to 0? In that case, well, when we first launched the system, let me just remind you very quickly, if you remember, if you recall, what we did earlier about the initialization events, right? You can see the init event over here, unconditionally will simply assign, or it will simply initialize the n variable to be 0, right? So that's something I can definitely quote as a special scenario, okay? So also think about another context which we need to consider would be when we initialize the system, n prime, the post state will simply just become 0, right? That's before after predicate that we spoke about earlier. So I can simply replace the n just to be 0 and n to be 0 over here, right? Okay, let me just be a little bit more picky about the color. So since we talk about that particular scenario where n is initialized to be 0, that's about init events, right? You can see exactly why I'm doing 0 replacement over here, because of the particular scenario when the reactive system was first launched. And now you can see 0 less than 0, false. 0 larger than 0, also false. Amazingly, we actually got false, right? For this. So if you try to evaluate this particular expression over here, oh, actually, you know what? Let me still use purple. If you try to evaluate this expression over here, it's going to be false. And of course, if you like, you can put a button over here to denote actually false. So this means both events are disabled, meaning that we got a deadlock. So what does that mean? Think about diagrammatically over here. So this is the abstraction which you apply for M0 model, the initial model. Let's think about the following scenario. When D is actually equal to 0, meaning that we can only get maximum 0 car, right? 0 cars on the island bridge compound, right? So you can think about this is the island bridge compound over here, right? Over here, and we are saying that the maximum value D, so any card you have basically will be less than or equal to D. That's basically what, that's one of the invariant, remember, over here, right? And to be more precise, it should be less than or equal to 0, right? That's basically the consequence of having this special value for maximum. And also about the initial value will be n is equal to 0 by the init events. So what we're having is, initially we are simply going to initialize the island and compound island bridge compound to have n is equal to 0. So n will just be actually equal to 0. In that case, are we able to actually allow either this event to happen or this event to happen, either one to really make progress? The answer is no, because the current value n will be 0. 0 less than the D, which we set, is also 0. So that means this is disabled, right? And also, if you try n over here, which is 0, 0 larger than 0, in order for you to really move into the island, in that case, we have no car to really move into the island, right? So either we cannot really go this way because this actually fails. This actually is this evaluated false. We also cannot go this way into the island. There's simply just no car, right? Let me say that again. I think I can put this better. Bear with me for the repetition. We cannot really go this way here because the maximum car that's allowed in this compound is actually 0. So no car can really enter this particular compound. That's why this was disabled. Similarly, symmetrically, we can also not go this way either because there's simply no car, right? Because n is initialized to be 0. In order to go this way, you must have at least one car so that you can go this way. So neither way is actually fine. Neither way is actually going to work. So that's why the system deadlock, right? I'm really trying to give you the intuition about how to interpret this fail sequence over here. Hopefully that's enough for you to understand. Right? I think that's about everything I want to say. And just make sure you understand, based on this, how we can actually come up with so many insights, into it. That's really the thing I would like you to pay attention to. Let's now go back to the slides, and everything I said on the notes has been mentioned. But I would suggest also take a look. The only thing I didn't include on my iPad notes was the init events over here, but you can definitely see that on the slides. And also I mentioned that already. Right? Let's now talk about what we should do. Knowing that our current model allows some unreasonable maximum value for the number of cars on the compound being 0. So we should really disallow that particular possibility, right? We should not allow D to be 0. Otherwise, we'll simply deadlock when the system was first launched. And the way to do it is not only that D should be a natural number, but also D cannot be 0, meaning that D should be strictly larger than 0. So what we should do is we're going to introduce this new axiom over here, which will be D larger than 0. Right? You can think about what we're doing is we're introducing this new axiom. We're going to say axiom 0, 2, and then D larger than 0. This will be the revision that we want to do. So this will be the revision based on the failed sequence. This will be the revision on model based on the fail sequence over here, right? It's really important to see the connection. And effectively, if you actually go back to the requirements number 2, which we spoke about 2 weeks ago when we first introduced the bridge controller system, we talk about requirements number 2 being the number of cards on the bridge and island is limited. That's all we said. But now, since we introduced this axiom over here, we are trying to help our customer who actually told us about the requirements to make it more elaborate, meaning that not only that it should be limited, but also it should be positive, right? That's what we have done. And since we have changed our model, so we have to reformulate our sequence for the proof obligation of deadlock freedom. Remember, the deadlock freedom also depends on the axiom. If you look at the proof obligation rule, let me show to you to be more 100% precise. If you go back to the proof obligation rule for, that's establishment, went too far back. If you look at the proof obligation rule over here, since now we have modified the axiom over here, so we have to regenerate the sequence for proof obligation for the deadlock freedom, right? It's a very straightforward idea. So having changed the context, the static context specifically, so we have to update the sequence that we want to prove. And the question is this new sequence now provable? Let's now find out, right? So this is really the proof that we did earlier but actually failed, right? You can see this is exactly where we failed. I'm going to use this existing failed proof to show you exactly what should be changed after this model revision. Just remember we are talking about the added axiom, which is axiom for model 0, number 2, d larger than 0. So this is the only thing that we actually revised, right? Just remember. Let's see exactly how the proof is going to be changed. First of all, we started with this proof obligation. That's what we're going to start with. Think about this one over here is the proof obligation for deadlock freedom, right? We started with this. So this is the proof obligation of deadlock freedom. All right, and since we are adding this particular axiom, so we're gonna introduce it, right? So you can think about this will go after this. So now we got two axioms. Not only that, d is actually a natural number, but also d is strictly larger than 0, right? That's how we start with. That's the only change. Accordingly, if we actually got this added axiom, are we going to be able to eventually discharge both branches? We'll see, right? Let's now go step by step. We're still going to actually rewrite this particular expression as n less than d or n equal to d, right? This part still the same strategy. So this one here, the same as this one over here, the same, right? Of course, we want to make sure we still have this axiom over here, right? This one will still stay there, right? It's the added revision. But if you look at the slides, I also show you the complete proof as well, right? But I'm now trying to show to you how to compare the proofs before and after the revision of the model. And now when we try to apply monotonicity, we want to drop everything except for the original thing that we wanted to keep, and also the new axiom for sure. If you drop this particular axiom, what's the point of doing the model revision, right? So you definitely want to keep this one as well. So what we want to do is, we definitely want to still keep the d larger than 0 over here. We want to keep that as well, right? So now we got this and this. We got two hypotheses, and then we got the goal over here. And we can split them by using the or left rule over here. If we do that, what's going to happen is we're going to split this disjunction over here. You can think about, let me try to make it more explicit for you. Let's say this guy over here is blue. So that means we got n less than d over here. And also this disjunct over here is orange. So that means this is what we have, all right? But for both of them, we should really keep any extra hypothesis. If you look at that, if you look at the original rule over here, let me show to you over here, right? We got the disjunction as the hypothesis, and any additional hypothesis should really remain in the separate sequence. You can think about the h over here the H over here is simply the D larger than 0 that we have, right? Really, okay? So we're going to keep this one here, D larger than 0, and also D larger than 0 over here, right? That's a split. And let's now try this branch over here where it used to be able to be discharged. Let's take a look. And for this one here, it's pretty straightforward, but now we got to be careful. You cannot really apply you can actually apply. After applying the OR R1 over here, we are keeping only this part over here, right? Let's now just make it explicit for you. So we want to keep this one over here, right? That's why we're using R1. Okay, that one's the same. But after this, we haven't dropped the hypothesis just yet. So if you try that, it's going to be D larger than 0 over here. Can we actually apply over here the hypothesis rule? We know that n less than D and n less than D is matching over here, the hypothesis and the goal. But we got some extra hypothesis over here. Can we apply this directly? Well, let me check together with you the rule. If you look at over here, this rule, we're saying that if the hypothesis over here matches the goal that we want to prove, there might be some extra hypothesis over here, which is our case, D larger than 0. That'll be okay. So now we don't need to drop this. We don't need to, right? So we can apply this directly. So let's now go back over here. If you really want to drop it, you can feel free, but you don't need an extra step. All right, so now we're done. So for this particular one here, you can see now we can simply just done. So let me mark a green over here. So this case, check as before. What about the second branch? So this is basically what we used to fail over here, but now we got some extra hypothesis thanks to the revision that we did into the model. Let's see if that will help. Right, so we're going to follow a very similar procedure. We're going to go for equation and then from left to right, meaning that we're going to, if you recall our, let me just show to you. So here we got n over here is the left, and also the D over here is the right, right? Left and right. Let me use pink maybe. Okay. So this will be the right over here, right? So what we're doing is we are trying to do equational substitution. So we're going to do from left to right, meaning that every occurrence of n is going to be replaced by D, right? So n is going to be replaced by D. So that's exactly this part over here that we have substituted, right? Only this part over here. And this part here as well, actually. And also this part over here, right? You can see the n over here is really substituted by the D over here, right? If I just want to be perfect in terms of the coloring, right? I think I should actually put green over here, right? The n over here, and also the n over here, the left, is going to be replaced by the right, the D over here, right? The left replaced by, sorry, the left replaced by the right over here. And then we're going to apply monotonicity to drop this equation, which already served its purpose. So that's what we have over here. But don't forget, we also got D larger than 0, right? So the monotonicity over here only drops this, right? Let me make a very important note over here. So here, this monotonicity only drops n equals to D. And that means we're still keeping the D larger than 0 over here. We're still keeping it, right? So after this, we definitely can see the matching over here. But now the question is, can we now apply the hypothesis rule? Can we? Let me just write it down over here. If you recall, the hypothesis rule, which is so useful for our deadlock freedom proof. If I have a sequence like this, some hypothesis, and then some, another one, and then turnstile P, right? In that case, by the hypothesis rule, I should be able to prove it automatically without any further justification. Let me just help you recall. But is our sequence over here really matching the hypothesis rule over here? Right? Let's try to see. D larger than 0 is really like the P over here. D less than D is really like the P over here. However, we got this particular disjunction that's really annoying us, right? So we cannot really, we cannot just yet applying the hypothesis rule, right? It's really important for you to understand this. Let me write it down over here. Okay, not yet ready to be apply the hypothesis rule. Not yet. It would be ready if we somehow can make sure the goal over here matches exactly this. So that means we want to drop this one. And we know that pretty well. That's exactly what we did earlier, right? So we can choose the or R2. So we're going to drop this, right? After we drop that, we got this one here. And don't forget, we also need to include this new hypothesis from the model revision, right? So that'll be d larger than 0. And awesome. So now we got this matching P. And also this alone entirely matches the same P. And we don't have any H over here. That's okay, right? So that means we can now finally apply the hypothesis rule. So we are no longer stuck, right? We are no longer stuck over here. So what we're going to do is we're going to say hypothesis, and we are done. Okay, so this case will also check. So this is a completed proof. And you can definitely, I try to give you the annotated version, especially try to combine and try to compare and contrast the failed proof that we actually did earlier. I think will be very beneficial. Of course, you can look at a complete proof in the slide as well.